Hey everybody, welcome to the intro video for our first digital lab for Marquette's COSC 2200/EECE 2710 Intro to Software and Hardware Systems course. So we're going to get started with digital logic today. What I've got with me is a benchtop power supply for supplying DC voltage, a solderless breadboard that we're going to use for actually producing our circuit, a set of jumper wires so that I can wire things up, as well as various assorted cables for plugging in the power supply. And then today we're going to have some other components that I'll show off in a couple minutes here, dip switch, LED, and some resistors, as well as our beginning logic gates. This is a pretty typical benchtop power supply that we're going to use for supplying DC voltage to our circuits. When you're ready to use it, power switch is on the bottom here. You've plugged it into the wall. When you flip it on, you're going to see both the voltage up here and the current down here. Current we don't really have to worry about too much for this set of lab assignments, but if it's cranked all the way to the left, just put it up somewhere in the middle and it'll be fine. The important thing is the output voltage. So these integrated circuits that we're going to use will have voltage range between something like 4.5 and 5.5 volts, but let's not push it. We want our voltage to be right in the 4.8 to 5.0 range there. So crank it to about there, and then leave the dials there for the rest of the time that you're working in the lab. So these are called banana plugs, and you should have one dark color for ground and one hot color for power, and those plug into little banana plug jacks in the bottom here. And then when you're ready to hook things up, you should have something like one of these little clippy guys here, or you might have alligator clip ends like this. And usually what we do is we run a couple of extra wires off the side of our power rails on our breadboard here and clip the ground and the power onto those leads when we're ready to go. Always double check your circuit before you turn on the power supply. All right. So this is our solderless breadboard. I have the solderful kind in my cabinet too if you want to see those. But for the kinds of work that we're doing, solderless bedboards are the way to go. So what you have here is a nice plastic case, and underneath there's a bunch of metal clips. So when you push a wire into one of these little holes, it makes an electrical connection. And so the trick is simply knowing what's connected to what underneath. So for these breadboards, you've got along the top and along the bottom two rails that we usually call power rails. So everything along the blue line here, what do we got? Five holes on the bottom there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 50 holes along the bottom here. Those all connect together. And so we'll normally connect ground to the blue rail, and wherever we need a ground reference in our circuit, we bring the connectors down to the blue rail. And then we usually use red for power. So you've got two power rails on the bottom side and two power rails on the top side. They are not connected to each other. They just connect along the board. In the middle section here, you've got columns of 5. So if you can see the numbering letter there, sockets 1A, 1B, 1C, 1D, and 1E, those 5 are connected together and not to anything else. Sockets 1F, G, H, I, and J are all connected together, but not anything else. So basically you've got 64 rows of 5 pins all connected together in these vertical columns, basically. This gutter here is what we call the indentation between them. Nothing connects across that, and so we use this for connecting together components like our dual load and line position, our dip switches, and our integrated circuits, because then you get the pins from one side of the circuit on the top and the pins from the other on the bottom, as I'll show you in a second. All right, so I'm going to start over on this end of the solderless breadboard. We're going to start with our first component, which is a dip switch, dual inline position. So you can see there's 8 little rocker switches on here. So they're either open, as it says down here, or when I switch the switch, that switch is now closed. So on the back side, we've got 2 rows of pins, and when I switch 1 here, I'm making a connection, closing between this pin and this pin. All right, So that's going to give me the ability to switch connections on and off. So I'm going to plug this into my breadboard here, right across the gutter. So I've got basically these columns here are going to be connected or not connected to these columns here based upon whether or not I've switched the switches. My schematic calls for a current limiting resistor here, so I'm going to take my 10K resistor, and so again, hold on the right way. You can see the gold precision stripe down at the bottom, and the color code is brown, black, orange, so that's my 10K resistor. And I'm just going to run it from the power rail to one of the switches here. I'm going to pick switch 5 in this particular case, just because that happens to be the right length for my wires. I'm going to take the bottom row of switch 5 and I'm going to run that down to ground. All right, so here's my switch circuit. I've got limiting resistor that goes from power down to the top side of the switch, and then from the bottom side of that same rocker switch, number 5, I've got a ground lead. So when I have a signal wire, such as my green guy here, that I actually want to produce a 1 or a 0 on, if I plug that into this row, ooh, there we go, I've got myself a nice little binary switching circuit here. So when the switch is open, the green wire is not connected to ground, but it connects to power through this resistor. So a nice clean digital 1 will flow into my green line here. When I switch the rocker switch, number 5, over, then I'm connecting the green wire to ground, and current will still flow from the power rail through the resistor, but ground wins when I've got a limiting resistor like this, and so I'll get a nice clean logic 0 going down my green wire. So to make my improved blinky light, the schematic calls for a NOT gate, an inverter, and so I'm going to use my first integrated circuit. So I've got here a little 14-pin chip. This is a 74 HC04, but what matters is that it's a 74 series, and the 04 tells me that this is a hex inverter, so it corresponds to the pinouts on your lab sheet. I don't know if you can see the lettering on the top there. It's kind of hard to read, but if you hold it at the right angle, you can see along the top it says 74HC04N. Don't worry about the N. So these little chips hold logic gates for us, and the way we use them on our solderless breadboard is we pick a set of columns and we press them on across the gutter like that, so that one set of pins is connected to the lower columns and the other set of pins is connected to the top set of columns. So every chip like this will have either a notch, see the little notch right there, or a circle, some kind of marking that indicates which side is which on the chip. Some will have both, but basically by convention, once your chip is in, find the notch, and the pins are numbered counterclockwise around from the notch. So this is pin 1, 2, 3, 4, 5, 6, 7, and then on this side, pin 8, 9, 10, 11, 12, 13, 14. All right? Also by convention, most of these chips, especially all of these 7400 series chips, we have the same pins for both power and ground. And this is one of the most important safety steps for using these gates. You have to have the power pin and the ground pin for this chip hooked up before you use the chip for anything else. So those should always be the first two connections that you make. And they always have their power and ground pins in the same place in this logic series. So I am going to plug in my chip with the notch facing to the left, and as I plug in more chips later on, I'm going to also plug them in with the notch facing towards the left, because I'm always going to run the power line up here to pin 14 and the ground line down here to pin 7. So same thing for this guy here, and again I'm going to use short leads, the correct length, so that they don't stand up and get in the way of stuff, and I'm going to try to, as best I can, use hot colors for my power rail and cooler colors for my ground rail. Okay, so this chip is wired up now, and when I power up the board, it's ready for me to use these individual gates. All right, so I've got my hex inverter wired in here. You can see the yellow lead is connecting pin 14 up to the power rail, and the green lead here in the bottom, the short green lead, is connecting the ground pin down to the ground rail. And I've used the dark blue lead to run the output of one of the NOT gates over to this row over here. So it's time for me to insert my LED. So my light emitting diode looks like this. Focus. So it's important to be able to tell which side is which on a light emitting diode. The two legs are called the cathode and the anode. And the cathode is the side that plugs in to the low voltage, and the anode is going to plug up to the higher voltage when we want it to light up. So usually you can tell by looking at the length of the legs. So the mnemonic I use is the cathode has the short leg, and that rests on the ground, and the long leg, the anode, reaches up to the power. But if your legs are already bent up and it's hard to tell, you can also tell by actually looking on the inside of the LED here. I don't know if you can see what's inside there, but the big triangular region, that's connected to the cathode, the part that goes to the lower voltage. So I can tell by both the large block on the inside and the shorter leg that it's going to go in like this. I usually bend my legs here, so it's super obvious which one is the cathode and which the anode. And we're going to put that into the board right like this across the gutter. And then I need a current limiting resistor because nobody likes to drink from the fire hose. So here I have my 1K resistor as called for in the schematic. So you can see the color codes there, brown, black, red. And I'm going to use that to connect up between the LED and the power rail here. So when the NOT gate in the inverter, which the input's coming from my green line here, reverses the 0 to a 1, that means there will be power coming on the blue line here. And so you'll have basically high voltage on both sides of the LED, which means the current will not flow and the LED won't light up. When you have a 1 coming in the green line, the NOT gate will turn it into a 0, a low voltage on the blue line, which means that there'll be low voltage on this side of the LED and high voltage coming from the power rail here, and power will run through the resistor and through the LED, and it will light up. So basically the LED will light up when my input here is a 1, and it will not light up when my input here is a 0. And so I get the inverted sense that, that I intended. Okay, so here we've got our breadboard set up with the improved blinky light. And so I've got my switch over here on the left, and my hex inverter here on the right, and the LED and its current limiting resistor here. So I've double checked my circuit. I'm going to power it on, and you can see the red LED turned on here. So I'm on switch number 5, and when the switch is off, not connected, my green wire here is producing a nice clean digital 1, and when I flip the switch to the on position, closing the connection, then the green line is grounded, and current flows through the current limiting resistor here, but ground wins, and so I'm sending a nice clean 0 through my green line, and the LED goes off. Okay, so that's it for side 1 of our Lab 1 sheet. That's the improved blinky light. So we have a nice clean digital switch interface for producing 0s and 1s, and an LED driven by the inverter, which protects the logic side of the circuit from the messy business of driving the LEDs. So next we need to duplicate the switching circuit so that we can have multiple switches for input, and duplicate the LED inverter circuit so that we can have multiple outputs, so we can actually see the truth table for several logic functions. So stay tuned, and we'll talk about that next.